Hey guys, this is the Orgo 1 exam review by the ACS. So who's be hosting is, my name is James, I'm the academic chair, and my assistant Kyle, who is not here at this time, will be the ones that hosting these ACS reviews. For the Orgo 1 exam 1 contents, we'll be talking about in a 75-45 minute ratio between Kai's exam and Ola's exam, which includes things like Lewis structures, condensed formulas, line angle formulas, resin structures, orbital hybridizations, acid bases, which includes things like Bronsted-Lowry's and Lewis acids and bases, polarity and solubilities, alkane/cycloalkane nomenclatures, Newton projections, chair conformations, radical reactions, and thermodynamics/kinetics. So we're going to go and get started with exam 1 from Dr. Kai, because that's been even the majority of us that will be struggling with. And then later on, once we have finished his entire exam, we'll go into Olaf's one of his featured or highlight exams. So for the first one right here, we have is three different nomenclatures. These three nomenclatures are always going to be alkanes or some sort of cycloalkanes in its term conformations. Other things we have to make sure we have to recognize is the fact that we actually know to know about the common names, or we can use this IUPAC names of substituents. Things like methyls, ethyls, propyls, the terp-butyls, the sec-butyls, the iso propyls, the neopentals, etc. So we're going to go ahead and break these down a little bit further by looking at these exam questions. So in this first molecule on the left, we have a parent chain of 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. And a bunch of constituents attached to carbon 2, 3, and 6. In carbon 2 and in carbon 6, these are known as methyl groups, which are basically just sticks with CH3s. So these are methyls. While the other one is also a methyl. For this big one over here at carbon 3, this is a propyl group because this actually contains 3 different carbons. So with 3 different carbons, you're going to notice that it's going to be a propyl group. But how it's bonded to the parent chain has to be what makes it a N-butyl or iso or a sect or a tert or a neo. So in this case with propyl, you have just propyl, which is just a standard 3-carbon chain, or isopropyl if it's sticking like a V-shaped tree, which it does. So we can name this as isopropyl, or we can name it in its IUPAC name, which is called methyl ethyl. So I'm going to put this in parentheses as methyl ethyl. That these are 2 acceptable names that you can use. So there's no stereochemistry, so we don't have to worry about the cis and trans for now. So our full name of this compound is, in alphabetical order, where we have to include iso, cyclo, neo, not di, tri, or tert, or sect. Iso counted, so I over M, we will have at carbon 3, iso propyl. And then we had to mention both 2 and 6. And since there's 2 of them, we have to notice that this is dimethyl. And then an 8-carbon chain is an oct. So we have an octane. That's molecule 1. Molecule 2, we have is a cyclo groups. That we have one that's on a wedge and we have one that's on a dash. So for this one, we have a parent chain, so I'm labeled as P. And we're going to have is a cyclohexane. For substituents, we have is this square right here and this dash. We know this dash from our previous molecule. That is our methyl group. So we're going to label that as a methyl. And the other one is a square, so it's probably going to be is a cyclobutane. And then for stereo, because stereo does apply in terms of cycle chains, we have as a wedge and dash. And usually we see that as a cis or trans. Cis versions are usually have a wedge and a wedge or a dash and dash. For trans, it usually has a wedge and a dash together. And since we see a wedge and a dash together, which means they're going in opposite directions, wedge means it's pushing it towards the front, it's pointing towards you, while the dash is saying it's pointing away from you at your plane. We're going to go ahead and have trans. So I'm going to go ahead and write that as trans. So it's going to be trans. And we need to make sure we need to number them too. And since we have a cyclo and a methyl, cyclo beats methyl. So we're going to put that as 1, and then we're going to put this as 3. So it's trans 1 cyclo butyl. So instead of ane, it's going to be a YL. Then we're going to have is a 3 methyl. Make sure you write this all in one line. I'm just running out of room. Cyclohexane. Okay. So for molecule 3, we have is another cyclo group that's in its chair conformation. So we definitely know that our parent chain has to be a cyclohexane. For our substituents, we have is a methyl group right here, and then an ethyl group right here. Why it's ethyl group is because there's 2 carbons sticking out. One of the common mistakes that people make when it comes to nomenclatures is that they're going to count this twice. So they think that's a propyl group. No, that's part of the parent chain. So when you count a substituent, you're counting it as an extension away from the parent chain. So that's why it's going to be 1 right here, and then 2 right here, and this is only 1 over here. So this is why I call this a methyl, and this one I call this an ethyl. Now we're going to go and consider stereochemistry. In shared conformations, you might be so uncomfortable how to read it. So a trick way to actually, translate between chairs into the original form is going back to its original cyclohexane form. So what I like to do is draw my hexagon right here, and I'm going to label as carbon 1 and carbon 2 because that's where my 1 and 2 going to be at. It's arbitrary, so you can just put it anywhere else you want to play. And I've noticed that going from this carbon 1, methyl is actually going upwards. So I portray that as a wedge. Well, on carbon 2, it's an ethyl group that's pointing downwards when attached to the cyclo. So that means I'm going to put this as a dash first. So like this. And you notice that it's similar to the ones to molecule 2. It has a wedge and a dash at the same molecule, which means that our stereochemistry has to be a trans. So we're going to go ahead and write our whole nomenclature name together. And it's going to be trans. Um, And again, numbering, E over M. So alphabetical order will actually determine the numbers. Once we actually find our substituents, order matters. So that means we're going to put this as carbon 1, and this one's going to be carbon 2. So now 1 ethyl, 2 methyl, cyclohexane. Okay. Our next question is about resin structures. So we have this molecule right here, and what we're going to do is we're going to draw all the hydrogen atoms attached to the line angle structure with the correct bond angles and orientation. So looking at this structure right here, we have as an oxygen, we have some double bonds, we have some positive charge. What we need to do is we need to show we have fulfilled the octet rule of Lewis structures and match what they actually correspond to. So I'm going to start off with the double bond right here, where we know that this has 3 bonds. So the 4th bond I just need is to add the hydrogens right here. And then for the carbocation, which you probably should have heard about what a carbocation is, it's a carbon with a positive cation formal charge. You would actually have just 1 hydrogen right here, flat on the plane of the molecule. And then what about with this one? Well, we need to satisfy the octet rule, and it's neutral, so it's going to have 4 different bonds. So there's going to be 2 hydrogens that's going to satisfy this, and it's going to be on a wedge and dash. So I'm going to have a wedge hydrogen right here, and at the same time, I'm going to have a dash hydrogen right over here. Indicate the lone pair of electrons in the above structure, which is already given to you by accident, but in order to show lone pairs, you just need to show that it fulfills the octet for the oxygen, because initially it only shows us as 2 of them. So in order to get the rest of them, you have to show the lone pairs to show the full octet. So there's the lone pairs right here. That's where you need to show up or indicate to draw them over there. Okay, so that's the first one. That's the second one. The third one is we need to indicate the orbital hybridizations other than the hydrogens in the above structure. So if we look at the structure one more time, we need to show what kind of orbital hybridizations we can actually do. So let's see. To represent the orbital hybridization of the structures, they usually have these bonds that correlate to what the molecular geometry of these molecules are. So looking at this particular molecule first, we do have four different bonds. We have one from each of the cation, one to the oxygen, and two from the hydrogens, though they are different atoms, well, the same atom, excuse me, but at different orientations, it still counts as a distinct bond. So that makes the sp2 3 for four bonds. So this is going to be an sp3. Okay. So the next one we're going to do is at the moment right here, we have this charge right here with three different bonds and then a lonely p orbital is just standing alone. For this kind of thing, because it's possible for it to rearrange the resonance, we're going to call that an sp2. So we're going to call that sp2. For these two over here with the double bonds, they are bonded three ways where the pi bond is not counted twice. So that means these two carbons right here is going to be considered as sp2 also. And then finally, for the oxygen at this particular moment, it's holding three different bonds. I meant to say four, not three, sorry. That there's going to be one over here, and then two lone pairs. So that means it's going to indicate this molecular geometry at that particular moment is going to be sp3. Now we need to draw the important resonance structures of the cation below, and we need to show the curved arrow to show the flow of electrons. So we're going to be using this molecule right here to show this because it's already been cleared. And the idea is that we need to push around lone pairs that will actually show different arrangements of the molecule below. So remember, when it comes to electrons that has double bonds, they're in that double bond of or the pi bond, as many people say. So what we could use is that we could arrange a way for that pi bond to be in a different place, so the electrons can flow on a different part of the molecule. So what I'm going to show is the arrow push, which is going to be a full arrow like this, that the double bond is going to move from this side to the other side, which means that one of them is just going to keep the electrons as is because it's just moving from one place to the other, while the other side is going to either gain the electron, so it's going to go back to a neutral charge, or it's going to lose electrons, so it's going to gain a formal charge. So this electron push in mind, actually, let me put this on the other side. We're going to have a molecule that looks like this. Positive charge, lone pairs. And that will look something like this. Is there a way we can actually make one more resonance structures? Actually, yes. These see that lone pair? We can actually rearrange this over here to form another resonance structures. So I'm going to go ahead and put that over here. Draw this again. Double bond right here, lone pair right here. And because it's only 5, not 6, it's going to gain the positive formal charge. All right. Lastly, what we need to do next is we need to circle the major contributor of the resonance. So to get the major contributor, we need to find two rules. The first rule is we need to have all of our bonds or all of our atoms, excuse me, to be a full octet rule. So that means four bonds or a total of 8 electrons fulfilled. And then if there are two resonance structures that ties and octet rules, then the tiebreaker is which charge is preferable for a particular atom. One good hint that many people should know is when you have a carbon that's positive charge or a carbon with a formal positive charge, that never satisfies the octet rule. So it has to be something other than carbon that has the positive charge or the formal charge, generally speaking, to have a full octet. So in this case, this particular molecule right here is considered the major contributor. Here's the third question. This is involving Bronsted-Lowry acids and bases. So there's three parts. We have these five molecules right here, and we need to draw the conjugate base and circle the least conjugate base. Then we need to rank the acidity from most to least, and then draw the resonance structures of the most stable conjugate base, if possible. So let's start with drawing the conjugate base. We're trying to take is an acidic proton, like Bronsted-Lowry's. That's the place where we actually donate the protons, because we're acting like acids. So let's go ahead and take these protons off. So I'm going to scratch out this, 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 and this. So I'm going to form a F3C, and then this O minus. That's the conjugate base. Then we have this again, the O minus and the carbonyl. Here, O minus. Okay, and then here, and then finally, that's the conjugate base. Now we also need to circle the least conjugate base. So the least conjugate base, I meant to say the least acidic or the least stable conjugate base. That's probably what I meant to say. So I'm going to go and correct that by fault. So then the least stable conjugate base is usually ones that has a concentrated amount of electron density on the conjugate base. So the one that has the most concentrations of the electron densities, where it just distributes or has an induction effect or some kind of S characteristics of orbitals, is compound E. Compound E is the most concentrated electron density towards the hydrogen proton. So that makes it the least stable conjugate base. So that will help us figure out the acidity of most to least. Because if that's the case with the least stable conjugate base, it's referably a pretty basic. So that means it's going to be the weakest acid. So we're going to label that as E is the far right. And then we're going to go ahead and go trending downwards. Comparing to these three can do resin structures. So I can actually just rearrange the distribution of the electrons, making them pretty acidic. So ABC must be a much higher acidity. But D, you cannot find a way to do resin structures. Even if we're able to do it, it would basically just make it more charged. So more charge would probably make it a little less stable to have that happen. So we're going to put actually D, which is known as a peroxy acid, to be the next least acidic. Now we're going on to the next three. So the next three is a bit interesting, that we're going to have resonance structures in all of these cases. What we need to figure out next is to figure out which one we want to uh, arrange in terms of more acidity. So which one would probably be the next acidic compound? So the best one in this case scenario would be compound B. Why would be compound B? So if you look at these three compounds on itself, all of them would have resin structures. They have ways to distribute or do an arrow push to the other oxygen to make resin structures. However, there is another part that is missing, and it's called the induction effect or the inductive effect. What it means is that we have some sort of very highly electronegative compound that pulls or quote unquote drags the electron density away from the molecule, causing the other side to be less electron density, readily wanting that hydrogen protons to just release, which is the definition of a Bronsted-Lowry acid. So if we don't have induction effect, then we don't have that availability for it to be much more acidic. So that's why B has to be the next acidic. So it's going to be the middle. Now between B and A, or sorry, C and A, they both have resonance, they both have induction. Now it depends on is how close are they? So to be this close, it makes it much more acidic because it's so closer towards the acidic proton that it actually has a much higher influence than uh it's when it's farther away. So it's going to be molecule C, and then oops, not a equal sign, and then it's going to be molecule A to be the most, and this is the least. Finally, we need to draw the resonance structures. Where's the pen? Resonance structures of the most stable conjugate base. So for the most stable conjugate base, which means it's the most acidic material, we need to draw the resonance structure. So we have our molecule A, F3C, O minus, and then O. We need to show the arrow pushing. So I'm going to do my lone pairs, push this, and since we cannot break signs because a carbon only could do 4 bonds, not 5, we're going to go ahead and push this back and to show that resonance structure looks something like this. And many people like to draw the brackets. I don't. You don't have to. It's just a way to show that these are related to each other. But many people like to do it, so I'll do that too. Okay, next one. So the next question is talking about the pKa of methane or methyl acetate. So the pKa of methane is about 50, and these are the approximate pKa values of methyl acetate. We have a pKa of 25 over here, and a pKa of 40 over here. Combining with CH3Li, which is lithium, which is a lithium meth, which is a lithium metal, lithium bonded to a methyl group. We need to go ahead first, draw the products of the acid-base reaction, and then we need to explain why and how. So, what's the product of the following acid-base reaction of methyl acetate and CH3Li? The product, when we actually react to this, is that this is a much more acidic, so this is going to donate the proton like a traditional Bronsted-Lowry acid. And the one that accepts it is going to exchange that by accepting the proton and releasing the lithium, which is a Bronsted-Lowry base. So it's going to do that double replacement reaction, as many people will see, and we're going to go ahead and see that by drawing this out. So it's going to be an H2C with a with a lithium metal on top. You can write that down or not. OCH3, which is a methyl group, don't worry, and then a CH4. So we have our products. Now we have to explain ourselves why the pKa of the protons of the OCH3 is much higher than that of the other protons of the methyl acetate. Well, if we actually drew and compare the two dissociated protons, so if I just look at this alone, H2C minus with this, and then we compare that with H3C, we can tell is that in this, if we actually try to move this arrow pushing on the peak, if we take an EG protein, the pKa of 40, we cannot move it. It's going to concentrate on that particular molecule. But if we actually put a hydrogen proton out from the left side of it, which has a pKa of 25, that's much easier because you can actually do resonance structures. You can actually form a resonance structure where it's just going to move around and guide for one beside the other through major contributors. So some of the points you want to make sure you do is to explain why the protons are higher than the other protons is that it's much more is that the electron density is much more concentrated on the OCH2 side versus a CH2 next to a double bond O, because it would distribute the resonance it would distribute the electron density through resonance. That makes it uh, least stable as a conjugate base, so it's going to have a higher pKa value. Next question is talking about solubility and boiling point. So we have to rank the following compounds that is going to be soluble in water, and we need to figure out the boiling point of each of these. We're going to rank them, okay? So let's start with solubility. So which one could be dissolved or could not be dissolved in water easily? Well, if you think about water, H2O, it's just pretty much, as many people would know, it's polar. H2O is polar. It has some undistributed charge. And what we're going to do is that we have to dissolve things that are basically like water. So things like hydrogen bonds and dipole dipoles, they're readily able to dissolve them pretty well in that situation. So readily, hydrogen bonds is what is much suitable. So we're going to put B as the most soluble. And then between A and C, C only have carbon and hydrogens, also known as a hydrocarbon. So it would be the least soluble in water, kind of like water and oil. And then A would be in between because of oxygen through dipole-dipole forces. Okay. Now for boiling point. So when it comes to boiling point, it really depends on the interaction of the intermolecular forces attached to it. So the higher the power of the intermolecular forces, the higher the boiling point is going to be. And the more branching, as in like there's more spread out where the surface area is decreasing, then you're going to have a lower boiling point. A good example is a tert butyl group or a dimethyl propane versus propane. So dimethyl propane is going to look like a cross or two methyls and a V versus just a V. That extra branching is going to make it uh, boil at a lower temperature than just a plain old propane. And it's already in its gaseous state, so it's readily going to be, you know, boil pretty easily. Well, or so that is probably at, or so that's actually a pretty bad example. But the idea is that if you have more things that just branch around rather than in a linear strain or linear stretch, it just has branches all over the place, then you're going to have a lower boiling point. So with C, with low dispersion forces, those are the weakest ones. So they're going to have a weakest one that's going to make them able to boil pretty easily. While hydrogen bonds are strong, so they're going to have a very high input to actually get them released to boil it out. So that's why water boils hard, but those things like propane tanks and other hydrocarbons boil pretty easily. So you probably will have a similar trend like this because dipole-dipole for the compound A is going to be, it's going to have to induce a few times, but it'll still be a lot more high, harder to boil. So it's going to be a much higher boiling point than those without the dipole-dipole interactions. Next question involves Newman projections. We need to draw a Newman projection at the first and second carbons of 1-bromo-2-methylbutane for both in this most stable conformation and this least stable conformation, the box below. Lots of words, be careful. So we're looking at the perspective of carbon 1 and carbon 2 of this molecule right here. So if you think about Newman projections, we are focusing on the carbon 1, carbon 2 bond. So we're looking at this direction. So I'm going to use is I have my eyepiece right here. I'm going to go ahead and look in this direction. In this direction, when I look at this, that means I'm going to have my bromine at the front so it's actually pretty much visibly at me. While on the back is all of the other stuff, which is the which is all of the C2H5 and CH3s. Again, this is skeletal formula, so we need to clarify it with more additional information like hydrogens. So we're going to have two hydrogens on the front on where carbon one is, but we're going to have one hydrogen that's on the back. So that makes it a clear enough visualization of what the molecule is going to look like. So let's go ahead and draw this out. Newman projections are the most stable conformation. We need to find a way to make the energy the lowest possible. And the way to do that is we had to put it in its anti-conformation. So an anti-conformation means that we have to be at least 60 or 180 degrees away from each other. That's like the farthest away possible for the most bulky compounds. So that bromine is a really bulky one because of the atomic radii. And then comparing to the other side of carbon 2, the C2H5, also known as an ethyl group, is a bulky material on the back of the projection. So we're going to have bromine at the front. So I'm going to draw this straight through over here. And we're going to have my two hydrogens over here. On the other side, we're going to have is my ethyl, methyl, and a hydrogen that's going to be surrounding it. But one thing you have to be careful about is that you have to be consistent on where they're located. So in order for them to locate pretty well, I have to make sure they're consistently on the same direction. So where they rotate, I have to make sure they're consistent. So I'm going to so one thing I need to make sure I put in is on the circle, not the dot, the circle, because that explains the back side of it. That's where I'm going to put in the most stable portion of it, which is CH, so not CH, C2H5 over here. And to be consistent, let's pretend that I'm going to have this as the front. So it's going to be like this. That means I'm going to have my methyl group over here. And then my implied hydrogen like this. They are independent from each other. They're the most farthest away as possible. And that makes them the most stable unit projection. Now, the least stable, put them is the opposite. Put the bulkiest materials and be as close as possible to them, which is known as an eclipse conformation. So I'm going to draw this again. Dot right here showing the front. Bromine, hydrogen, and hydrogen. Gonna put another wedge right here, and a wedge right here, where I need to put my uh, ethyl group right here that's close by, my CH3 on the other side, and then a hydrogen right here. That will make it very, very um, less stable because it's very crowded. Steric hydrogens is going to interact, so it's going to give us a higher energy. Our next question is nucleophiles and electrophiles. So this is basically a general statement of what our Lewis acids and bases are. So Lewis acids and Lewis base has their own terminology, which is basically means electron rich and electron poor. So the ones that are electron rich are Lewis bases. They are known as nucleophiles. They are the ones that actually will do the attacking that's going to grab those electron pores, Lewis acids, electrophiles. So electron rich, nucleophiles. Electron poor, electrophiles. Nucleophiles are Lewis acids, and electrophiles are, sorry, nucleophiles are Lewis bases, while electrophiles are Lewis acids. And what usually you see every time, and especially when it comes to things like mechanisms and such, which you'll learn that in the future, you curve arrows always shows what's called a nucleophilic attack, which means that the double bonds or any electron-rich mechanism, electron-rich uh, compounds will always attack electrophilic, electron-poor Lewis acids compounds. So the first thing we need to do is we need to draw the product. So to draw the product, we need to put them bonded together. And what we need to do is, I'm just going to draw this out, is that these are together. So there's a synthesis, a reaction of a cycle, a molecule with an alkene. I'm going to put a BH3 right here. So that gives the bond, but at the same time that lost the bond. So that means I'm going to have to put in the intermediate of a formal charge. Now, the next one I need to add is I need to know which reactant is a Lewis acid and which one is a Lewis base, and then include the mechanism of the reaction that I have to show the curve arrow pushing. So the double bond is actually the Lewis base. Then the BF3 is a Lewis acid. Now, how can I tell very easily? Well, the double bond does contain pairs of electrons. So that means so these pi bond is going to have some electron density. So it's electron rich, making the Lewis bases and nucleophiles. While at BF3, if we draw the Lewis structures very carefully, we have these three bonds to the boron. but the boron wants to have an octet, which it doesn't because there's always an exposed empty p orbital. So it's electron poor, making that a Lewis acid. Okay, so now we need to indicate the mechanism of the reaction using curved arrows to show the flow of electrons. So to show the flow of electrons, we need to show that nucleophiles attack electrophiles. So that's where we actually have our arrow pushed towards the electrophile. So like this. But we're going to go ahead and do this a little bit more precise. So I'm going to go ahead and take this double bond right here, and it's going to attack the boron right here because that's the one that is electron poor, not the fluorine itself. So that's why you want to indicate people. Make sure you point which molecule you want to point, so that way that indicates what product you're going to make. Okay. Draw the most and least stable of the cis 1-ethyl 3-isopropyl cyclohexane. So we're going to draw a cycle in its IUPAC way or the flat plane way to make sure I have like a picture of what's going on. So at carbon 1, which I'll label as carbon 1, and then I'm label carbon 3 right here because this is 2. I'm going to have an ethyl group and an isopropyl group at carbon 3. One thing you need to know about is that this is a cis. So that means I need to put them at the same orientation. So that means I'm going to have double wedges, or I have double wet or double dashes. You cannot do a wedge and a dash because that is a trans. Now, what I'm going to do is I'm going to turn them into chair conformations. It's hard to draw chair conformations. The one that I've been taught or I have been doing is basically try to make a down arrow and up arrows that just barely miss each other. And then I just drew it like this. Try that again. Which takes a lot of practice. But another way you could do this is taking parallel lines. That'll work. And then we're going to do the chair flip. That'll look like this. We need to draw the most and the least stable version of these. So I'm going to draw them first and see what they are. So what I'm going to do is I'm going to put carbon 1 right here, carbon 2 right here, carbon 3, 4, 5, and 6. And then over here, 1, 2, 3, 4, 5, and 6. So let's start with the left one. At carbon 1, we have our ethyl group, so it's going to point upwards. The carbon 2, it's nothing, so it's all hydrogens. And then carbon 3, it's going to go up. So it's going to go like this. Sorry, that's a little messy. All right, and then 4, 5, 6 is just all hydrogens, so there's nothing to change. On the other side, where we have our ethyl group at 1, it's going to point like this. And then a carbon 3 is also going to point like this. So which one is the most stable and which one is the least stable of this curve conformation? Well, to make it least stable, interaction must happen when they're actually on the axial positions. And there will be no interactions when these substituents are in equatorial positions. Axial positions are the ups and downs of the chain conformations, while the equatorial positions are the ones that actually point outwards or away from the chair. So looking at the left chair, we have them on axial positions because it's pointing upwards. And axial positions do interact to steric hindrance because it's so crowded, making this side, the left chair, the least stable. Which means on the other side, with both materials at the equatorial position, they're not going to interact as much as they want. So they're going to be pretty much relaxed, and they're going to be the most stable chair conformation. The next quadrant is talking about thermodynamics. So thermodynamics is all about the energy bonds. So this is all the stuff that involves breaking bonds and forming bonds that's increasing and that's going to decrease the bonds. That's what it's talking about. So what's described here is the second propagation reaction. This needs an A. In the bromination of methane. And we need to actually add a heat of formation using the table bond associated energies. They will give it to you on like the reference chart on the back of the exam. So don't worry if I just spewing numbers. So when it comes to this reaction, we're going to have is a BR. And a BR is going to do what's known as homolytic cleavage. So it's going to form what's called bromine radicals. And that means we break the bond, so we get our delta H, our energy change, to equal to positive 45. And then the unit right the unit's right here, kilocalories per mole. But now we have bromine radicals over here that's going to form the CH3Br. So that means we have is a methyl radical and a Br radical to form a CH3Br. Since we form a bond together, it has to release energy. And when you look at your table, which is delta H, this has to equal to negative 72 kilocalories per mole. So the overall estimated heat of formation should equivalently equal to minus 27 kilocalories per mole. So with just the second propagation reaction in mind, is this reaction endothermic or exothermic? So the reaction, when it comes to the enthalpy, if it's negative, it's exo. If it's positive, it's endo. And since just this focus on this propagation step is a negative value, this means that we're going to have is an exothermic reaction. Okay. So then we need to draw the transition state and then show that it's a product-like or reactant-like, and then which two partial bonds is stronger. So the transition state of actually forming this bond is basically like this. We're going to have to put this in a bracket together. The bromine distinctly going to lose this bond like this. And then distinctly, this is going to be next to a CH3. Okay, back to transition state. And so because it's exothermic, through Hammond's postulate, the transition state has to resemble what's going to look like, what's going to look like in that direction. So the transition state for this exothermic reaction is going to be reactant light. Why? It's because that if we have a net negative overall of the reaction by thermodynamics, in this case exothermic, we're going to have Hammond's postulate telling us that the transition state is going to look like the reactant side. So then now, which two partial bond is much stronger? Well, if it's preferred to be reactant, then the bromine radical before the homolytic cleavage is stronger. Oops. So then our final Chi question is involving radical reactions. So don't be scared about the radical reactions. This is just basically a simple reaction question. If you guys hadn't gone over it, just save this as like a good extra note. So we have is a product to make by using a hydrocarbon compound with bromines and light. So remember the steps of initiation, propagation, and terminations. We have to basically break down the bromine into bromine radicals. And then with the molecule at hand, we need to take a hydrogen off to form the HBr, of course, and then the bromine radical and the radical itself of the product would form the actual um, product by radical reaction. So then how can we tell? Well, with light, so we have bromine already here, and then for the carbon compound or the hydrocarbon, we want to put the radical on its most stable position. And the reason why we say that is because it's very regioselective. It's very selective in choosing on which place they want to do. When compared to chlorine, by Hammond's postulate, we'll choose pretty much almost any position. So with bromine specifically, we're going to have it on the most stable radical position, which is going to be over here. And combining with the bromine radical, so I'm going to scratch this into a bromine radical. This is going to bond together. This is the mechanism, by the way, to form this molecule together. And that is the end of the Chi sample exam one. Now I'm going to go ahead and switch to the mindset of Dr. Olaf's exam one samples. So for Olaf's exam samples, here are some highlights that they or his exams features. Things like Newman projection that looks like this. We have orbital hybridizations and drawing geometric correct line angle structures. And one of our favorite ones, Lewis structures. So I'm going to start off with this one. We're looking down at the carbon 2 and then carbon 3 bond. We're going to need to draw the Newman projections of all these staggered conformations of what's called a 2,3 dimethylbutane. That's our molecule. And we also need to circle what the most stable energy conformation is. Okay, so we need to find the most stable Newman projection of 2,3 dimethylbutane going through carbon 2 and carbon 3. Okay, so at carbon 2 and carbon 3 of 2,3-dimethylbutane, which means we're going to have a 4-carbon chain with a dimethyl, so it's 2,3-dimethyl, so carbon 2 and carbon 3, that is our molecule, okay? And we got to stare it down at carbon 2 and carbon 3, which is right here and right here. So I'm going to use my eyepiece, looking at this position, and find that I'm going to have 2 methyl groups on this side and 2 methyl groups on the back side. And I want to make sure I get the most stable or the lowest energy conformation. So let's go ahead and try this. So I'm going to use CH3 right here, and then an H right here. And on the back side, we're going to have is a CH3, a CH3, and a H. Here's a trick when it comes to doing projections. Keep one side, the front, or the back still. So like keep it through the entire way, while the other side needs to rotate every time. So every 120 degrees, switch our positions by rotating clockwise or anti-clockwise. So I'm going to do the front side and I'm going to keep everything like that. So CH3 and CH3 and H, and then CH3, CH3, and H. Now, we're going to rotate the backside. So we're going to have a CH3 over here. And I'm going to do this clockwise. So CH3 right here, which that's not formally correct bonding ways. So it's going to be H3C. And then this is going to be H. And one more rotation. We have an H, a CH3, and an H3C. Okay, so we have all of our Newman projections. Now we need to figure out is which side is the most stable. And the most stable is basically we have to make sure we have less interactions to each other. And looking at the middle one, it seems like there's actually the least interactions compared to these two, which are about the same, where they have half of the entire human projections being interacted on the front and back. So the most stable or the lowest energy conformation in this human projection is going to be this one. Now we're going on to a geometric like correct line angle structure and orbital hybridizations. So you're given this chart, this string of letters, NCCCCOCH2OH. The idea is to make sure that you actually know the geometric structure, specifically if you know their bonds. Remember, all of these molecules must satisfy their octet rule and neutral. So let's start off with the left, and then we'll go start from the right. So if you look at this one right here, I can tell that in order to satisfy the octet for these two together, C must have a single bond and then a triple bond, because it has to be the most neutral ways possible with nitrogen. So NC, then we have a C right here, and then over here is another C, so we're going to have to do another triple bond, and then another C right here. So we already covered 4 C's, so this is gone, 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 gone. Now we got to go to an O and then a CH too. So that means we're going to have to take an O right here and a C to make it the most neutral as possible. Because it's already taking one bond right here, but we need another one for carbon, another one for oxygen. We need to make sure that we actually fulfill this octet by covering every possible way to get that four carbon ring, a four carbon structure, four carbon bonds. There we go. Then we have two H's right here, and then an OH. Okay. So now with the geometrically structurally sound materials, we can actually figure out the rest of the problems. But let's draw the geometric correct structure. So we have is a nitrogen right here, the lone pair, triple bonded to a carbon, then single bonded to a carbon, and then triple bonded to a carbon, then single bonded to a carbon, and then it's going to be double bonded with an oxygen, then a carbon, gonna put my dashes, my wedges, or my two hydrogens, okay, and then mm, and then an OH. Simple as that. Well, not quite, because I need to make sure it's geometrically sounded. So I need to go ahead and erase this because my carbon oxygen is not 120 degrees. So I'm going to do this. And there we go. Okay. So then now let's answer the other part. Write the state of hybridization for each of the two indicate atoms in the boxes provided. This one is talking about the second carbon. So this one right here, well, since it's linear and 180 degrees with a triple bond, it has to be with an sp orbital hybridization. And then the other one right here with an oxygen, well, we can probably put the lone pairs right here. Make sure, right, just to take out the hydrogen. Remember, geometrically sound. That means we can have some kind of sp3 orbital hybridization. Okay. Now we need to know how many sp3 hybridized nitrogen atoms are in this molecule. Well, this is our nitrogen right here. It's linear, so it's sp. So that means there is actually 0 right here. And then how many sp2 hybridized atoms are in this molecule? sp2? Well, we have only one of them, which is that C-double-bond-O. So there's only one of them. I should also mention that was a mistake. Uh, there's one carbon atom that is sp2. But the overall picture of this is that we have the oxygen that's also sp2. And again, this is why there's too many errors of not checking your lone pairs. So make sure, like I did with Kai's exam, you have your lone pairs structured. So the actual answer is actually two. When we have one carbon that's also sp2, and then one oxygen atom that's sp2, with a total of two different atoms that are sp2 orbital hybridizations. And then our final question, we're going to draw some geometric correct Lewis structures, including charges, lone pairs, and radicals of each of these six parts. So the first part is telling us we need a tertiary radical uh, with a formula C4H9. So we need a tertiary radical, which means it's paired up with other three molecules on its own. So we're going to have is a carbon right here in the middle with a radical with other three carbons together. The formula is C4H9. So what we can do is we can put it in distributes of three, CH3, CH3, and CH3, and we have C4H9, and that is our molecule. Our second one is asking us the molecule with the formula C5H12 containing only quaternary and primary carbons. So quaternary means that it's a four bonded carbon, and the primary means it's bonded to only one carbon. So we need C5H12 with only quaternary and primary carbons. I can think of only this because this one gives me a quaternary, and then we have the other four. So then with all of them as CH3s, that will give us the 12 hydrogens we need. Okay. Next one is we need the most stable resonance structure of CH2N2. One of the things I've noticed when it comes to Lewis structures is that usually the first atom that's been read, CH2N2, is typically the central atom. So we're going to have the carbon right here attached to two hydrogens and then a nitrogen. Okay. The problem with this is that we need to actually do this with, we need to find a way to arrange this to where it's the most major contributor. So if we did like this, well, then we have a positive formal charge, and then this one's going to be a negative formal charge. That's not great. So let's go ahead and put this as a double bond instead. All right, so that will satisfy the octet rule. This one would be neutral. Well, this one's going to be a minus, minus charge. Okay. What about putting the minus charge over there instead? So now we could, let's go ahead and do that. Then we have our lone pair right. Then we have our lone pair right here. And so that would make it a positive charge, and that would make it a negative charge. And how would that work? Well, it would actually work because it actually has the octet was fulfilled. And the charges, they don't matter in terms of which one's positive or negative, although they do matter in terms of where they're positioned. So with this major structure, that has to be the major contributor because of the octet rules. The other parts of it, where we have the carbocations and carbanions, it's possible, but it would not satisfy the octet rule, so it wouldn't be a major contributor. Part D, go check these off. We need a molecule with the formula C6H6, which contains only sp2 hybridized carbons. So we need a six carbon chain that only contains sp2 hybridized carbon. That means all of them has to be at least a double bond or something. And one of the ones that came up pretty easily, that I thought, would be this group. Six carbons, six hydrogens, and all sp2 hybridized. Okay. The next one, an isomer of CH3, CH2, COOH with the lower boiling point. So I'm going to go and draw this out, see what this is. So it looks something like this. That's our reference. What we need to do is draw a different isomer that has a lower boiling point. And my thinking would be is take a metal off and then switching it like this. So now it's going to be looking like this. And then finally, part F, let me actually go back to part E actually. Why is that a lower boiling point than the one over with the reference one? The reason why is because of intermolecular forces. So if you look at if you look at the COH, this OH is going to be affected very well in terms of the boiling point because of hydrogen bonds. So hydrogen bonds being the strongest intermolecular forces, making the boiling points a lot higher. Then with a lower boiling point, by having no hydrogen bonds, that is a possibility for it to go down. So with this H and the methyl group switch to make this compound right here, then it only has dipole-dipole forces. The dipole-dipole intermolecular forces, making the boiling point lower than the one with the OH that will cause hydrogen bonds. And finally, part F, a molecule containing four chlorines that has no dipole moment. Okay, so no dipole moment. Well, the one that came up to my mind is that having a carbon with four CLs. Each individually has a dipole moment, but the overall molecule containing this has no dipole moment because they're all symmetrical, making it non-polar. Okay, so that is the end of the recording and the PowerPoints of your exam ones. I would say good luck to you guys on your exams and hope you guys do well. And thank you guys for watching, and you see you guys the next exam.